Hi kids, welcome back to these videos. This one is gonna probably be a bit of a long one, so hopefully you guys have your jammies on and some popcorn or whatever it is that makes you coziest while you're taking notes on these videos. It's on conservation of charge and the way we get charges on objects, charging. So we talked a little bit about the word charge in the last video, but we're going to be going into a lot more detail in this one. The variable we're going to use to represent charge is a lowercase q for no good reason. It just is what it is. And the units of charge are the coulomb, which is named after a person who did a lot of research into electrostatics. Coulomb can be abbreviated capital C, and it's not made up of any other units because it's a fundamental unit. It's just a property that objects have. The vast majority of charged particles in the universe are protons and electrons, which we talked about before. There are some other charged particles, but they're not going to appear in this class. Maybe if you take more physics down the road, you'll learn about them. And for our purposes, we're going to assume that protons have a charge of +1 coulomb apiece. This isn't strictly true, however, it'll work for this class, and you'll learn more details down the road. Electrons have a charge of -1 coulomb each. We said in the last slide that protons were positive and electrons are negative, so each proton is 1 coulomb, an electron is equal but opposite, so -1 coulomb. So the charge in the universe is conserved. Total net charge in any closed system is going to be conserved, but of course the biggest, most closed system out there is our universe. And by coincidence, it turns out there are exactly as many protons as there are electrons in our universe. And I say by coincidence because there's no sense that this needed to be the case in what we understand about the Big Bang. There could have been vastly unbalanced numbers of protons and electrons in the universe. However, if that had been the case, the universe would have been ripped to shreds. Matter could not have coalesced like it did into planets and stars. So it's a really nice coincidence that there happen to be exactly as many protons as there are in electrons, because it means that life as we know it is capable of existing. Which means that the net charge of the universe is 0, right? So the word net, just like we used it in our last unit for forces, means add up all the forces, positive and negative. In this case, we're adding up all the charges. If we have exactly as many protons as we do electrons, add them all up, the net charge of the universe is 0. So although the net charge in the universe is 0, you can have a non-zero net charge in a smaller system, because we can have moved charged particles in or out of a small system. In other words, smaller systems can have temporarily unbalanced number of protons and electrons. The net charge of a system is going to be the total charge of the protons plus the total charge of the electrons. We can always calculate that for any system just by adding up all the protons and the electrons. So for example, in this little system, we have an insulator here with 4 protons and 3 electrons in it. So we might say that the Q net, or the net charge of this system, is +1 coulomb, because we have +4 and -3. So we're left with a net of +1. This is a small amount of positive charge. We could have another system that looks like the following, right? Same insulator, but this time we have 4 protons and also 4 electrons. In this case, the net charge, or the Q net, is 0 coulombs, or neutral, because we have exactly the same number of protons as we do electrons. We could have a case where we have a negative net charge. If that insulator with 4 protons has 7 electrons in it, then we would have a Q net of -3 coulombs, which is a larger net charge than that first positive net charge, because we have a bigger amount of leftover. In this case, it happens to be a larger negative charge. Okay, so we know that the universe as a whole is neutral, but that individual parts of the universe, little small systems, can have a net charge. So how do they get that net charge? Well, they start with balanced numbers of electrons and protons, but we can move those electrons in or out of the object. A little reminder, the electrons are spinning around the outside of the atom, and they can be grabbed or pulled or pushed. However, the protons are stuck in the nucleus, and usually protons don't move. If you pull a proton out of the nucleus, what you get is a nuclear explosion. So in this unit, if you find yourself moving a proton around, please try to remember that unless you're dealing with a nuclear explosion, the only subatomic particle that can move around, the only particle that can make an object get a net charge one way or the other, is an electron. So there's many different ways we can charge an object by moving those electrons around. And the first thing we're going to talk about is something called polarization. You'll notice the root pole of that, just like the north and south pole, means dividing something into halves. And so what happens in polarization is we actually have two objects to start. We have an object with a net charge, a large net charge already. We'll talk about how it got that in a little bit. And then we have an object with a neutral net charge overall. So the one on the left obviously has a lot of extra electrons. That's going to be negative. The one on the right should be neutral. We have 4 protons. We need to add 4 electrons, but we're going to wait a minute to do that because you'll notice that the one on the right is a conductor, which means those electrons can go anywhere they want. So the question is, if I was going to put 4 electrons into that neutral object on the right, where would they want to go? Well, normally they'd kind of spread around and hook up with those protons that are in there. But in this case, since we have a whole bunch more electrons nearby in this negative object over here on the left, those electrons, when we put them in, don't evenly distribute themselves. In fact, they put themselves as far away as they can get from these other electrons, because like charges will repel each other. So because they are all negative, they're all going to go as far away as they can, as far away as possible. So what we end up with here is a neutral object that has a positive half and a negative half, right? This is the negative half. We've got 2 extra electrons on that half, and this other half is the positive half. We have 2 extra protons in that half. Sorry, my pen's not working very well. So even though the object is neutral, we are polarized with 1 part positive and 1 part negative. Interestingly, polarized objects can actually be attracted to charged objects, and the reason is because each half experiences that electrostatic force. That positive half on the left is attracted to the negative object nearby, and it's very close. It's closer, so it has a strong attraction. The negative half is repelled, but since it's further away than that positive half is, it's not repelled as strongly as the positive half is attracted, which means that overall, that whole neutral object is attracted to the negative or whatever charge the other charged object is. And we'll do a number of demos to show you guys that this is true in class. So as far as getting those charged objects in the first place, there are 3 main types of charging: friction, contact, and induction charging. Friction charging occurs when you rub 2 different insulators together, and it transfers electrons from one to the other. You're all probably familiar with friction charging, right? When you rub your feet on the carpet or rub a balloon on your hair, those are all examples of friction charging. So we've got 2 different insulators. They're both neutral to start, which means we have this balanced number of protons and electrons in each one of those insulators. When you rub them together, what happens is one of those insulators just happens to be a material that likes electrons a little bit better than the other one. And so it will grab electrons off of that other insulator. Now, insulators don't like letting go of their electrons, but if another insulator feels even more strongly about it, when you rub them together, you let those atoms get close enough that they can actually snatch electrons off of each other. So a little bit of a comment here. You'll notice the electrons are not flowing when the electrons that are grabbed are all from the very surface of the insulator, and they stick on the very surface of the insulator that grabs them. They don't move freely through those insulators. They end up sticking pretty much right on the edge wherever they're grabbed. So when you're done, we were both neutral when we started. When you're done, you end up with 1 insulator that has a positive net charge. The green insulator has 5 extra protons because it lost 5 electrons, which means it has a net charge of plus 5 coulombs. And the orange insulator has 5 extra electrons, which means it has a charge of negative 5 coulombs. So in the universe, we're still conserving our charge. We just have transferred it from one object to another. There's a chart known as the Electrostatic Series that basically says how strongly an insulator feels about electrons. So the further those objects, the insulators are towards the negative side of this, the more it likes to grab electrons, and the further it is towards the positive side on this chart, the less it likes to hold on to its electrons. So if you rubbed rubber on glass, for example, the rubber is definitely going to grab all the electrons from the glass, so glass ends up positive and rubber ends up negative. If you rub cotton on plastic, the cotton ends up positive and the plastic ends up negative. We'll do some examples of this in class as well. You don't need to have this memorized. I just thought you should know that when it comes to determining which insulator ends up with the electrons, there's just this chart that basically tells you how strongly they feel about grabbing electrons. The second kind of charging is called contact charging, and this happens with conductors. If two conductors that have unequal charges are brought into contact, the electrons move until both conductors have the same charge. Little asterisk there, but for the purposes of this class, that's an okay assumption. So if I start with two conductors that have unequal charges, so the one on the left has a charge of +6 because we have 6 extra protons, and the one on the right has a charge of +2 because it has 2 extra protons. When you make contact between those conductors, what happens is those electrons basically spread out as far as they can. Okay, the electrons in the conductor on the right would rather be further from each other, so they move on to the conductor on the left. There's also a lot of extra protons on the left over there, so those electrons on the right see those protons and they say woohoo, and they run over to the other conductor as soon as they have a path to run. So since these are both conductors, it's really easy for those electrons to move anywhere they want. So when we're done, we have a net charge of +4 for each conductor. If you wanted to figure out what that charge could be, of course, it's just the average. So if we have a +6 and a +2 before, you average it all out, you end up with +4 for each of those conductors after we're done. You guys may have heard the term grounding before. It is not when your parents make you stay in your house. This is a different kind of grounding. It's actually a form of contact charging that is contact charging between a charged object and the ground or the earth. So what happens in grounding is you connect an object to the earth with some kind of conductive wire. So I take a metal wire and I connect an object to earth, and what that does is Earth is basically this massive, enormous conductor that has as many electrons and protons as you could ever need. So when you connect an object to it, those electrons and protons can flow on or off of the Earth depending on what the object wants. In case you have wondered what, in your electrical outlet, if you've got those 3-pronged wires, that round wire in the bottom is called a ground wire, and in your house it literally goes usually up to the roof and then down on the side of the house, and then someone has drilled a metal stake into the ground near your house, and that provides kind of a safety route for electrons to take. If we have too many electrons somewhere, it provides a route for those electrons onto the earth that is safer than going through you or somebody else that might be in the way of the electrons. So that's what that third wire is. It's grounding, but if you hear the word grounding, it just means connecting a conductor to the ground or the earth. And the last kind of charging is called induction charging, and it's definitely the most complex. In induction charging, you start off with an neutral conductor. Okay, so I have a metal ball right there that has no charge. The first step so induction charging, the idea is that we want to get that object, that neutral object, a charge without touching it. Okay, so we're trying to charge an object, a conducting object, without contact. So the way you do it, you start off with that polarization that we learned about before. So I can take a negative or a positive object and bring it nearby, and when you do that, you end up with a polarized conductor. Okay, so now my conductor is still neutral, but it has a positive half and a negative half because the electrons have moved. I don't like that picture well because it kind of shows the protons moving. We know the protons don't move, but the electrons will all move away from that negative object that's near it. And then the next step is you ground the conductor. So you put a wire connecting that conductor to the earth. And in this case, what happens is all of those electrons that were on the conductor, we're trying to get as far away as possible from that rod right there, and so they actually ran off the conductor onto the Earth. Okay, so those electrons escape. And then if you take off that ground wire, so we no longer are connected with Earth here, right? We got rid of that in step D. And then in step E, you remove that negative charged object. What you're left with is a positive charged conductor because all the electrons went to Earth. So you'll notice those 4 extra electrons are on Earth, which Earth doesn't really notice that because there's so many electrons on Earth, but because the conductor is relatively small, we now have a positive net charge on that conductor, and we never had to touch it to another conductor. We never had to touch it to a charged object in order to charge it up. So this is an interesting kind of charging. It's really useful in the real world. Industry does this a whole bunch, and we'll be doing some examples of this one in class as well. But it takes a lot of steps. All right, we made it. Quick summary of what we covered in this lecture. The number of protons and electrons in the universe is balanced, but you can move electrons from one object to another. And what that does is it gives each object an equal but opposite net charge. Polarized objects are neutral, but they have a negative half and a positive half, and they can experience force as well. There are 3 kinds of charging. Friction charging, which rubs electrons off of one insulator onto another. Contact charging, which allows electrons to flow from one conductor to another until they are balanced. And the last kind is induction charging, and that charges a conductor without contact. This might be a video that you want to go back and take your time watching twice, double check your notes, because there's a lot of dense material in here that we'll be using in a lot of different ways in class. Thanks for your time.